So we just examined how to obtain these values of the intercept and slope. What we do is we minimize the sum of squared errors, and we call that the least squares method. Now in practice, you won't have to actually calculate by hand the sum of squared errors in most instances. Nearly all modern statistical software, it'll fit classical linear regression or simple linear regression, and it will use this method of least squares as the default. But it's important to keep in mind all that it's really doing. All it's doing is it's finding the intercept and slope through this criterion, through this idea that in general you want the observed raw values of your outcome to be pretty close to the fitted or predicted values. So you want the y and the y-hats overall to be pretty close to each other. And the way we do that is we take all the errors, all the residuals, we square them, we add them all up. We want that one quantity to be as small as possible. Conceptually, just like the visualization tool that we just outlined. Now, as a consequence of this least squares method, of this particular algorithm or criterion, we have some unique properties of the simple linear regression line. Right? And we're going to look at some of these in just a moment. But before we do, you might want to ask, why is regression even called regression? Why is it called this? Well, it dates back to the first prominent use of simple linear regression by this guy, Francis Galton. And here's Mr. Galton himself. And he wrote this wonderfully titled paper on height and mediocrity, he talked about. And he was looking at inherited stature. He was looking at height. And Galton, he was this British statistician, he was a sociologist and pseudogeneticist, and he wrote this paper called Regression Towards Mediocrity. Right? Mediocrity, it's really, he was talking about regression, what we call regression towards the mean. The term regression, that word, it's based on these Latin words of gredi, which means to walk, and then back. So it means to walk back. So it's walking back towards the mean. That's where Galton came up with this idea of regression. And we'll look kind of what this means in terms of regression. In Galton's analysis, what he did is he looked at what he called the midpoint height of parents in inches. So he was just kind of like basically using sort of one measure that encapsulated the height of both parents. And he used this measure of height of a child's parents to predict the heights of children. And he wanted to see the degree to which height led to the height of children. You know, do tall parents tend to have tall kids? Do short parents tend to have short kids? So he came up with this idea of linear regression. And he found that if you have very tall parents or very short parents, then the kids will what he called regress to the conditional mean, or mediocrity in Galton's words. To put another way, if you didn't have very tall parents, well, that children will be taller than average, but that children probably won't be as tall as his or her parents. If a child has very short parents, then that child will probably be shorter than average, but probably won't be as short as that child's parents. So you can kind of think of it as the Einstein effect. You know, Einstein was a brilliant guy. He had kids, but we have never heard of his kids. His kids are probably pretty smart, but they're probably not as smart as Einstein. So let's see if we can replicate Galton's findings using his actual data. So this is Francis Galton's data set, and we have all these different variables, and we're going to look at height. So the idea here is we're going to predict the height of a child based on the mid-parent height. This is sort of you can think of it as kind of like an average height of both parents. And we're going to see, can we predict the height of children based on the height of parents? So we have this output from statistical software, and we get these coefficients, these values of the intercept and slope. These are the least squares values for the intercept and slope. And we can see by minimizing the sum of the squared errors, we get an intercept of 22.38, and we get a slope of 0.64. So recall, how do we interpret the intercept? What it does is it tells us that if the parental height, if the mid-parent height is 0 inches, then the expected mean height of a child is 22.38 inches. Keep in mind, the intercept may not always be substantively meaningful. In this case, it doesn't really make sense to talk about having a parental height of 0 inches. Right? Conceptually, what's actually going on is that we're extrapolating far beyond the range of the data. Right? The most of the data, it's going to be in the 50 inches and above range. We're extrapolating all the way out to 0 inches. So the intercept, it locates the line in the scatter plot, but it's not always substantively meaningful. How do we interpret the slope? Well, recall that the slope tells us the rise over the run. Right? So for every 1 inch increase in parental height, the expected mean height of children increases by 0.64 inches. Now, you can kind of think about, this is where the quote mediocrity, end quote, comes in. This is the regression, because it's not a perfect relationship. Right? You can see that if you have, for every 1 inch increase in parental height, right, it's passed on to the children, but not perfectly. Okay? It's a 0.64 slope. Right? So you can see it's a positive linear relationship. So taller parents tend to have taller kids, but those kids tend to be a little bit shorter, right? Or they tend to be a little bit taller. And we'll look at this in just a moment. Here is Galton's data as a scatter plot with the simple linear regression line fit through the scatter plot. So you can see it's a positive linear relationship. And that least squares line, that's the line that minimizes the sum of squared errors. But let's extend the x-axis out to 0, and let's remove the point so we can visualize the intercept and slope. Here is the intercept. So when x is 0, when the mid-parent height is 0, the expected outcome, the expected height of children is about 22.38 inches, which is, it's a nonsensical value because it's so far below the range of the data. But it locates the line through this scatter plot. And then we get this rise over the run. So for every 1 inch increase in mid-parent height, we have this increase in the height of children of 0.64 inches. Right? So let's use this model for predicting or describing. So let's look at tall parents. What would you predict the height of a child if she had parents with a midpoint height of 74 inches? So if the parents had this sort of midpoint height of 74 inches, what's the height of a child? Well, let's use our regression model. And we can see that the y-hat, the predicted height of children, equals the intercept plus the slope times the raw value of x, which is the mid-parent height. We plug in our values of 22.38. That's from the least squares output. And we have a 0.64 for the slope. And so thus we can predict by putting in 74 inches that the height of a child, if the parents are 74 inches, the height of the child, we predict the expected mean is going to be 69.74 inches. So we can see this visually. So this is sort of the upper range of the data set. So the mid-parent height is 74 inches. We go up to the line, and we can follow across. And we can see that the expected height, the mean height conditional on that value of x, is about 69 inches. Well, let's predict the height for short parents. What would you predict the height of a child if she had parents with a midpoint height of 66 inches? Right, so that's shorter, on the shorter end. So we can use our simple linear regression model. We just put in a value of x. What we're doing is we're calculating the mean of our outcome conditional on a particular value of x. So what is the mean of our outcome when x equals 66? Well, we can predict. Right? So we plug in the value, and we find that if the midpoint height of the parents is 66 inches, then the expected mean is 64.62 inches. So we can visualize this. So this is the child with parents of 66 inches, and the child's height we predict is, a little bit shorter, but it's within the ballpark. You can see here a pattern when we compare short versus tall parents. The short parents have a height of 66 inches, while the tall parents have a height of 74 inches. That's a difference of 8 inches. The tall and short children have an expected mean height of 69.74 inches and 64.62 inches. That's a difference of about 5.12 inches. You can see that this is where you kind of have this walking back towards the mean. If you have very tall parents in this data set, you're likely to be tall, but you're not as tall as your parents. Right? If you have very short parents, you're likely to be shorter than average, but you're not going to be as short as your parents. So you can see here we have this idea that we are, we're kind of regressing in a way to the mean. Okay, so if you have, you can see that we have this sort of regression of the mean. Now, one important consequence of this is the method of least squares. You have particular properties of the intercept and slope. So recall that the values of the intercept and slope are just obtained by minimizing the sum of the squared errors. There are several interesting properties as a result of minimizing the sum of squared errors. You can fit other lines. These other lines won't have these properties. So these properties are very useful with regards to the intercept and slope. So let's look at some of the least squares properties of the slope. That is, by minimizing the sum of squared errors, we get several interesting characteristics or properties of the slope. So by minimizing the sum of squared errors, we obtain a slope with this equation. This should look somewhat familiar to you. We're just using the sigma notation. But if you look at the numerator and compare with the denominator, right, all we're doing is we're calculating the sum of the cross products of x and y. So that's similar to what we examined in covariance. And we're dividing by the sum of the square deviations of x. Right? So the denominator is simply a raw values of x around the mean of x. And we're squaring them so they're all positive. Well, as the numerator, it's in essence capturing that part of x and that part of y that covary together. And conceptually, that's really what the slope is telling us, right? So the slope in the simple linear regression model, it's equal to the covariance of x and y divided by the variance of x. So the covariance of x and y is a measure of how x and y go together, and the variance of x is sort of the overall variation in our input or predictor variable. And conceptually, this should make sense because what the slope is telling you is for every 1 unit increase in our x variable, how does our y variable change? And it encapsulates the information that x and y covary together, but it's scaled by the total amount of variation in x. Right? So you can think of when we minimize the sum of squared errors and we have the least squares estimate of the slope, we have a covariance of x and y divided by the variance of x. Right? With the Galton data set, we can find that the covariance of x and y is 2.12 and the variance of x is 3.30. So you can just calculate this by hand. The slope equals 2.12 divided by 3.3, which is 0.64. That's exactly the same as the least squares value of the slope. This is just identical, right? The least squares properties of the intercept are also useful and interesting, as by virtue of minimizing the sum of squared errors, we have an intercept that can be expressed in this way. The intercept equals the mean of y minus the slope times the mean of x. You can think of the intercept, it's the difference between the mean of our outcome with the weighted mean of our predictor or input variable, where the slope is actually the weight. Think about what happens as that slope gets larger or smaller. Right? That value of the slope times the mean of x, it's going to shift the intercept upward and downward. So let's look at this. For the Galton data, the least squares intercept is given by 66.76, that's the mean of our outcome, minus the slope times 69.22. That's our mean of our x variable. That's the mean of the mid-parent height variable. We might ask, what would happen if the slope were 0? Then the intercept would equal the mean of our outcome. And that reflects the idea that the slope is 0, then you just have a horizontal line, and it crosses the y-axis right at 66.76. And that also reflects the fact that you can interpret the intercept as the expected mean of the outcome when b1 is 0. Then you might ask, what would happen if the slope were very large and positive? If it's very large and positive, then the intercept would shift downward, right, because you're subtracting. So what's happening, and that makes sense, because if the slope is very large, that intercept has to shift down. Okay? You might also ask if the value of the slope were large and negative. All right? Then it's going to shift the intercept upwards. Okay? So you can see that all that's going on is that the intercept is shifted upward and downward based on the value of the mean of y, the mean of x, but also that value of the slope. Right? And that should make intuitive sense. So to recap these properties of the intercept and slope, by virtue of minimizing the sum of squared errors, we have an intercept that is equal to the mean of y minus the slope times the mean of x. And then we have a slope given by the covariance of an x and y scaled by the variance of x. Right? To put it another way, you can take the cross products of x and y and divide it by the sum of the squared deviations of x. And that will give you the least squares value of the slope. You don't actually have to calculate the slope by hand or the intercept by hand, but the key point is that both of these can be expressed in a very simple way, just in terms of the covariance and variance. And the other key point is that both the slope and the intercept from the least squares regression line, they are based on the means of x and y. And this is an important point, because the intercept and slope are based on the means of x and y, they are sensitive to outliers. Right? In the same way that the mean of x and the mean of y, those are sensitive to outliers, in contrast to, say, the median, the 50th percentile. In a similar way, the intercept and slope to the least squares regression line, those are going to be sensitive. Because they're using the means of x and y, they're going to be sensitive to any sort of outliers. Okay? So things to know for this discussion of the sum of squared errors and the least squares properties of the intercept and slope. The values of the intercept and slope from simple linear regression, they're obtained through the method of least squares. By minimizing the sum of squared errors, the intercept and slope and the predicted values, they all have particular properties. And especially important properties at the intercept and slope, they're based on the means of x and y. And with that, for our next discussion, we will talk about how you can actually decompose the variation of the outcome and how you can actually measure the fit of your least squares line to a particular scatter plot of data.